You know, we often obsess over product design. We look at a new smartphone or an electric car, and we kind of imagine these geniuses in a pristine white room, just agonizing over every single curve and button.
Right. Planning exactly how it's going to change the world.
Exactly. But history is, well, it's messy. Sometimes the most influential products in history weren't actually designed to be products for us at all.
That is the classic happy accident theory of innovation. I mean, think about penicillin or the microwave oven or Post-it notes.
Post-it notes are a great example. But today, for our deep dive, we are looking at a video game that totally fits that category. It's a title that killed an entire generation of hardware and basically defined the architecture of the Atari 2600.
And yet it wasn't even supposed to be a game.
No, it was just a diagnostic tool. It was literally code written to make sure a computer chip didn't catch on fire.
We're talking about Video Olympics, of course. Released in September of 1977 as a launch title for the 2600.
Right, and you are going to love this deep dive because we are pulling from a massive archival report we have here. It covers the engineering logs, the executive summaries, technical analysis, the whole vitals of the project.
And if you read through these engineering logs, it becomes super clear that this was not some passion project.
No, it was a stress test that got completely out of hand. A stress test that accidentally became the very first true party game with this wild 50 games in one concept.
It really is wild. But to understand why Video Olympics had to happen, you have to understand the absolute panic that Atari was in around 1975 and 1976.
The pre-2600 era. So this is the age of the dedicated console.
Exactly. And that entire business model was a massive dead end. Back then, you'd buy a plastic box that played Pong.
Just Pong.
That's it. It played Pong. If you want to play Tank, you literally went back to the store and bought a completely different plastic box that only played Tank.
Which is just insane to think about now. It's like buying a separate DVD player for every single movie you want to watch.
It was completely unsustainable. I mean, once a kid got bored of Pong, the hardware was essentially trash.
Right.
So Atari buys this think tank called Cyan Engineering to build a new project, codenamed Stella. This was going to be a microprocessor-based system that could play any game using interchangeable cartridges.
And that project eventually becomes the Atari 2600. But the executives at Atari were really nervous about this, right?
Oh, terrified. They were moving from hardwired circuits, which they fully understood, to software and CPUs, which was basically black magic to business executives at the time.
Right, because with the old machines, the game was the circuitry. Now the game is invisible code.
Exactly. So management handed down this incredibly strict mandate to the engineers. They said, this new Stella system absolutely has to replicate our two biggest arcade hits.
Pong and Tank.
Pong and Tank. If it couldn't perfectly replicate those two games, management was going to kill the project.
So the entire fundamental architecture of the Atari 2600, the machine that eventually brought Pac-Man and Space Invaders into millions of homes, it was designed specifically just to play Pong.
It was explicitly designed around those very specific constraints. The custom graphics chip they built, the television interface adapter, or TIA, was hardwired with logic gates meant to draw a ball, two paddles, and the tanks.
Wow.
And this is where a guy named Joe Decuir enters the picture. He was a young electrical engineer hired specifically to debug these Stella prototypes. He actually co-designed that TIA chip with J Miner.
So his job wasn't to make a fun game.
Not at all. His mandate was just to prove the chip actually worked.
Because J Miner would send the chip designs to fabrication, and when the physical prototype chips came back, someone had to verify them.
Right. You can't just look at a piece of silicon under a microscope and know if the math is working. You have to run code through it.
So Decuir writes a program, basically an engineering checklist.
He writes a very raw, basic version of Pong. He just needs to verify the logic. Can the chip read the paddle controllers? Check.
Can it track the ball?
Check. Can it detect when the ball sprite hits the paddle sprite? Check.
But this is where the big shift happens, isn't it? Because unlike the older dedicated machines, which were just physical wires soldered together, he was working with software now.
And that is the huge aha moment. Decuir realizes that because he's using a microprocessor, he can parameterize all the game logic.
Parameterize it,
Yeah.
meaning he can easily change the rules.
Exactly. In the old days, if you wanted the ball to move faster, an engineer had to physically swap out a resistor on the circuit board. Now, Decuir just changes a variable in his code.
He effectively builds a physics sandbox for himself. He can change the ball speed, the gravity, the size of the boundaries just by typing in a different number.
That's it. He realizes that by tweaking these parameters, he can create a soccer mode. Tweak them again, now it's hockey. Then handball. Then basketball.
Volleyball.
Right, he wasn't writing new massive blocks of code for every single game. He was adjusting the variables in the physics engine that he had built to test the chip.
That is just incredible efficiency. He literally turned a mundane debugging session into a giant library of sports games.
And it just kept ballooning until he had 50 distinct variations. And eventually, Bob Brown, who was the director of microelectronics, saw this test program running in the lab.
And he saw the dollar signs.
He realized they didn't just have a diagnostic tool anymore. They had a massive retail product. So he told Decuir to just cap it at 50 games, wrap it up, and they would ship it.
So Video Olympics is literally Joe Decuir's homework assignment.
Pretty much.
But I want to get technical for a second, because if you look at Video Olympics today, it looks incredibly primitive. It's just blocky squares on a flat background. But the archival report we're looking at suggests that getting those simple blocks onto the screen was an absolute nightmare.
Oh, it was a miracle of resource management.
Oh.
You have to look at the hardware specs to appreciate it. The 2600 ran on an 8-bit MOS 6507 CPU. It ran at 1.19 megahertz.
Okay.
But the real crushing limitation was the RAM. The system had exactly 128 bytes of RAM.
Wait, 128 just bytes.
Just bytes.
Not kilobytes, not megabytes.
No. To give you a modern perspective,
Yeah.
a simple text message you send on your phone is probably larger than the entire working memory of the Atari 2600.
So if you have virtually no memory at all, how do you even display an image? Because normally a computer draws the entire screen into memory, what we call a frame buffer, and then sends that finished picture to the monitor.
The Atari had no frame buffer. It was impossible.
Yeah.
It couldn't remember what the screen looked like because it didn't have enough RAM to store even a single line of pixels, let alone a whole screen.
So if it can't store the image, how is the TV showing anything?
This is the core philosophy of the Atari 2600. The programmer had to do what they called racing the beam.
I love that phrase, racing the beam, but I want to make sure I really get what that means physically. We're talking about the electron beam inside a big, heavy, old CRT television, right?
Yes, an old tube TV works by literally shooting a beam of electrons out of a gun in the back. That beam scans across the glass screen, left to right, top to bottom, drawing lines. It does this 60 times a second. The Atari CPU had to calculate and generate the color and position of every single pixel in real time, cycle by cycle, just nanoseconds before that physical electron beam hit that specific spot on the glass.
That sounds incredibly stressful. It's basically like laying down the train tracks while the train is rushing up right behind you.
That is the perfect analogy. If your code is too slow, even by a tiny fraction of a millisecond, the beam passes you. The screen goes black, the image completely tears, or the whole game just crashes. You are perfectly synchronized to the physical reality of the television set.
Which brings us to arguably the weirdest thing about Video Olympics. It's a 4-player game. I've seen the quadra-Pong modes, but you just told me the TIA chip was hardwired specifically for Pong.
Right, 2 players.
So how are there 4 paddles on the screen at the same time? Is Decuir just performing magic here?
He is breaking the physical rules of the hardware. The chip can only draw 2 player sprites, 2 missile sprites, and a ball. That is the physical limit of the silicon. So Decuir used 2 major hacks to get around it.
Let's hear them.
First, he used the missile sprites. In a game like Tank, a missile is just a tiny 1-pixel dot, but the hardware has a register that lets you stretch a sprite out horizontally.
Wait, so he took the tiny bullets?
And he stretched them out to look exactly like paddles. Yes.
That is brilliant.
So player 3 and player 4 are actually playing as stretched out bullets.
Wow. But what about the games where you need vertical paddles? You can't stretch them that way, can you?
No, you can't. And that required his second hack, a technique called multiplexing, or flickering.
Oh, I've definitely noticed that in old Atari games, where the characters sort of violently shimmer or blink.
Exactly. That is the programmer tricking your human eye. The chip can only physically draw 2 vertical players. So on the first frame 1/60th of a second, Decuir's code draws player 1 and player 2.
Okay.
Then on the very next frame, he rapidly moves those sprites across the screen and draws them as player 3 and player 4.
So the 4 paddles are never actually on the screen at the same time?
Never. They literally take turns existing. But because it happens 60 times a second, your brain's persistence of vision basically blends them together into a single image. It creates this ghostly flickering effect, but it genuinely allows 4 people to play simultaneously on a machine explicitly built for 2.
It's basically a forced optical illusion holding the game together. And he has to manage all of this, racing the beam, flickering the sprites, calculating the physics, while also reading inputs from 4 different controllers.
And those paddle controllers were not simple digital buttons. They were analog potentiometers.
Which means what for the code?
Think of the dial on the paddle like a dimmer switch on a dining room light. Or even better, think of the controller as a bucket of water with a small hole in the bottom.
Okay, a bucket. I'm with you.
To figure out where the player has turned the knob, the Atari sends electricity to fill the bucket. It charges a capacitor in the controller. Then the console literally just counts how long it takes for that bucket to empty out. If the knob is turned all the way to the right, the electrical resistance is higher, so the bucket takes longer to empty. So the CPU has to just sit there and count 1, 2, 3, until the voltage drops below a threshold.
But hang on, if the CPU is sitting there counting a bucket emptying, how is it also racing the beam? It can't pause the TV to check the controllers.
It can't. And that is the genius of Joe Decuir. He had to perfectly interleave his code. He would tell the processor to draw a few pixels of the screen, then quickly check the bucket, then run back and draw a few more pixels, then check the bucket again. Doing that for 4 players simultaneously without crashing the television display is a massive coding feat.
It puts a whole new perspective on those blocky graphics, honestly. It wasn't primitive design, it was intense resource triage. Okay, so we've got the technical foundation, but let's actually talk about the game itself. Because Video Olympics wasn't just Pong, it introduced some serious gameplay mechanics to the home market.
It absolutely expanded the vocabulary of video games. Before this, Pong was just simple geometry. The angle the ball comes in is the angle it bounces out. But Video Olympics brought in 3 key mechanics: whammy, catch, and jump.
The whammy. I love that name. It sounds like a secret cheat code.
It was essentially a physics modifier. In the original arcade Pong, once the ball left your paddle, you were helpless. You just had to watch it. The whammy let you add English, or spin, to the ball right at the moment of impact.
So how did it work?
If you press the controller button at the exact frame you hit the ball, the code would apply a sharp vertical offset to the ball's trajectory. You could essentially slice it or max out its velocity.
So it changes it from a game of mere prediction into a game of aggression. You can actually fake out your friends.
Exactly. And then you had catch. This mechanic allowed you to hold the button down to put a magnetic grip on the ball when it hit your paddle. You could catch it, carry it up and down the screen, and fire it back when you were ready.
Which is huge, because it stops being a passive tennis match and starts being something closer to a modern sports game where you actually control the pace of the play. Possession.
Right, and then jump was used in the volleyball modes. You hit the button, and your paddle would instantly teleport higher on the yay axis to spike the ball.
Yeah.
But beyond those mechanics, the thing that really stands out in the report is the single-player mode, Robot Pong.
Yes, because writing artificial intelligence on a machine with 128 bytes of RAM sounds literally impossible. How smart could this robot actually be?
It couldn't be smart. It had to be strictly efficient. Decuir couldn't afford to have the computer constantly tracking the ball's movement across the screen. That requires too much math for the CPU while it's racing the beam.
So what did he do?
He used bounding box logic.
Meaning?
The computer opponent essentially goes to sleep and ignores the ball entirely while it's traveling through the middle of the screen.
Yeah.
It only wakes up and runs a calculation when the ball physically hits the top or bottom wall.
Oh, I see.
Yeah, it calculates the bounce, predicts the final destination on its side of the screen, moves its paddle there, and then just waits.
Wait, but that gives the human player a massive edge, doesn't it? If the robot completely stops paying attention to the ball mid-flight.
Yes. Remember the whammy mechanic?
You can whammy the ball after it hits the wall.
Exactly.
Yeah.
If you slice the ball and change its angle after it bounces, the computer doesn't notice the change. It just goes to the blind spot where the ball should have been, and you score an easy point.
You can literally exploit the AI's blind spot.
You are outsmarting the constraints of the code. And that Robot Pong AI has an amazing legacy. Jump forward to 1999. Developers were putting together a compilation of classic Atari hits for the PC, and they wanted to include the original 1972 arcade version of Pong.
Okay, but the 1972 arcade machine didn't have a single-player mode.
Right, it was strictly 2-player hardware. There was no AI to copy.
So what did they do?
They went deep into the Atari archives, dug up Joe Decuir's code from the 1977 Video Olympics cartridge, reverse-engineered his bounding box AI, and grafted it onto their arcade simulation.
That is fantastic.
So even today, if you boot up a modern digital version of classic Pong and play against the computer, You are very likely playing against that exact 128-byte brain that Decuir built.
The code survived. I love that. Now we have to pivot to the business strategy side of things because as fascinating as the engineering is, Atari didn't release this cartridge out of the goodness of their hearts. The archival report literally calls Video Olympics a corporate weapon.
It was a strategic nuke aimed at the rest of the industry. You have to picture what the electronics shelf space looked like in 1977. It was absolutely flooded with cheap Pong clubs.
The dedicated consoles we were talking about earlier, you had the Magnavox Odyssey, the Coleco Telstar, dozens of knockoffs from companies nobody remembered.
Right, and those cost maybe $50 to $100, and they played one or two games. So here comes Atari launching the new 2600, and it is expensive. It costs $199.
Which is practically $1,000 adjusted for inflation today.
They needed a killer value proposition to justify that massive price tag. Video Olympics was their main weapon.
Because of the parameterized code.
Yes. Because Decuir had figured out how to squeeze 50 distinct game variations onto one single cheap cartridge, Atari's marketing department got to print 50 games in one, in huge letters on the box.
It makes the consumer math so simple. Why would you ever buy a plastic console that just plays hockey for $50 when you can buy a $20 cartridge that plays hockey, soccer, basketball, and 47 other modes?
It instantly made the entire competition look like a complete ripoff. It made dedicated consoles obsolete overnight and cleared the lane for the programmable cartridge era to take over. And to make sure it worked, Atari made a crucial partnership with Sears.
Ah, right, Sears. And for our younger listeners tuning into this deep dive, we really need to emphasize that Sears wasn't just a dime clothing shop in a mall back then.
Oh no. Sears in the 1970s was basically Amazon. If your product wasn't featured in the Sears catalog, you effectively didn't exist in mainstream middle America.
Right.
And Sears had previously partnered with Atari to sell the original home Pong console. So Sears practically owned the brand equity in the minds of consumers.
Pong was the household name. Atari was still a relatively new concept to most parents.
Exactly. Pong was like Kleenex or Band-Aid. So Atari strikes a brilliant deal. They sold the game themselves under the title Video Olympics. But they gave Sears the right to sell the exact same cartridge with the exact same code under a completely different name, Pong Sports.
Pong Sports. Which explains why you see both of those cartridges out in the wild today for the same game. It was just different branding to capture that core Sears market.
It was a brilliant, dual-pronged attack. And speaking of the branding, we really have to talk about the box art strategy.
The Cliffstone artwork, it really is iconic.
It is incredible. But it wasn't just pretty. It served a vital psychological purpose. Look, when you boot up the game and look at the TV screen, you see a square white dot bouncing between two rectangular white lines. It's highly abstract.
But when you look at the physical box...
When you look at the box, you see this gritty, dynamic, beautifully painted montage of real athletes, sweating, jumping, diving for the ball.
It's what the report calls the imagination gap.
Exactly, the imagination gap. In 1977, the graphics card wasn't actually inside the console. The graphics card was in your brain. The box art provided the rich visual data, and the simple blocks on the screen provided the kinetic motion. You, as the player, had to synthesize the two.
The art essentially tells you, hey, this glowing rectangle is a professional hockey goalie. And because the gameplay mechanics, the sliding, the fast bouncing, actually kind of felt like hockey, your brain just filled in all the missing visual fidelity.
We really demanded a lot more from the player's imagination back then.
Yeah. We've definitely lost a bit of that magic, haven't we? Now a modern game renders every single bead of sweat on a player's forehead. You don't have to do any cognitive work at all.
We've definitely traded imagination for pure fidelity.
Well, before we wrap up this deep dive, I want to hit the myths and trivia section of the source report because there are some fantastic cocktail party facts in here. Starting with the game timer. Why do the timed matches in Video Olympics last for exactly 2 minutes and 16 seconds?
It is such a bizarrely specific number, isn't it? 2 minutes and 16 seconds. It actually comes directly from the arcade hardware.
The original coin-op machines.
Right. The old arcade machines didn't have software to keep time. They used physical hardware counters. Specifically, a 13-bit binary counter that ticked at 60 hertz, tied to the TV's refresh rate.
Okay, lay the math on me. How does that equal 2.16?
So a 13-bit binary counter can only count up to 8,192 before it literally runs out of bits and rolls back over to zero.
Okay.
So if you take 8,192 ticks and divide it by 60 frames per second.
You get 136 seconds, which is 2 minutes and 16 seconds.
Precisely. The length of a game of Pong was entirely determined by how high a cheap piece of silicon could physically count. But Decker deliberately kept that exact same time limit in his software version for the home console.
Why keep it if he didn't have to?
Because culturally, it turned out to be the perfect length for a match. It was just short enough that kids had to frequently pass the controllers around the room.
It was a built-in anti-hogging feature.
It was unintentional parenting assistance baked right into the code.
I love that so much. Okay, next up, there is a very persistent rumor that I need you to squash. You see this on forums constantly. People claim that Carol Shaw, the famous creator of River Raid, programmed Video Olympics.
Yeah, we really need to correct the record on that one.
Mhm.
Look, Carol Shaw is an absolute industry legend. She was the first female professional game developer at Atari. She programmed River Raid and 3D Tic-Tac-Toe, but she did not join the company until 1978.
And Video Olympics launched in September '77.
Exactly. The timeline doesn't work. The myth actually comes from bad internet data scraping. Modern emulators analyze the ROM files, and they see that Shaw later programmed a sports game called Polo. So automated systems just conflated the early bat and ball genre with her name.
But the source code is clear.
It is 100% Joe Decuir.
Good to know. Credit where credit is due. Okay, one last historical detail from the report. The legal trouble.
Ah, yes, the Amateur Sports Act of 1978.
Which did what, exactly?
It turns out the U.S. Olympic Committee is intensely protective of the word Olympic. The act gave them exclusive rights to the term in the United States.
Oh, so Atari naming their flagship game Video Olympics was suddenly a major liability.
Very much so. Luckily for Atari, they released the game just before the act was strictly enforced, so they weren't forced to recall the thousands of cartridges already out there. But it made that Sears partnership incredibly valuable.
Because the Sears version was just called Pong Sports?
Exactly. Pong Sports was a much safer bet legally. It's why you see the Pong Sports branding persist heavily in later catalogs. Atari really didn't want to get sued into oblivion by the actual Olympic Committee.
It is truly amazing how much pure history is packed into this one single cartridge. You have hardware engineering, you have corporate retail strategy, and you have federal legal drama.
It represents the defining bridge between two massive eras of technology. Video Olympics took the hardwired physical logic of the arcade, the physical circuits and solder, and proved it could all be extracted into pure software.
It proved that a general-purpose processor could handle the twitch reflexes of an action game.
Yes, it was the proof of concept for the entire multi-billion-dollar home software industry we have today.
Well, I want to leave you, the listener, with a final thought to chew on after this deep dive. We talked earlier about those flickering paddles, the way the player's sprites violently blink in and out of existence to make the four-player mode work.
The multiplexing hack.
Right. Today, if we saw a character blinking like that in a game, we'd immediately call it a glitch. We'd say it's bad graphics.
We'd go online and complain and wait for the developer to patch it.
Exactly. But if you really think about it, that flicker is actually evidence of the programmer fundamentally breaking the laws of physics defined by the hardware. It is the visual signature of pure ambition.
I completely agree.
It's Joe Decuir pushing a 128-byte machine to do something it was explicitly never built to do. So when you sit down and play a modern game that runs flawlessly at 4K resolution and 60 frames per second, maybe ask yourself, are we missing a little bit of that pioneer spirit? That sheer excitement of seeing the seams burst just a little bit because the idea was simply too big for the box it came in.
That is a wonderful way to look at it.
Thank you so much for joining us on this deep dive into Video Olympics. Go dig an old CRT television out of a garage, grab a couple of friends, and we will catch you on the next one.